Welcome to the class of stochastic processes. We continue the coupon collecting problem. The question is, what is the expectation of the number of types that appear only once in the complete collection? We know some types of coupons may appear only once, but some types of coupons may appear more than once. But here we are interested in the expectation of the number of types that appear only once in the complete collection. Here is the solution. We let II be 1 if there is only a single type I coupon in the final set and 0 otherwise. So this question can actually be mathematically formulated as the expectation of summation II. And we can bring the summation outside the expectation. So summation of expectation of II. And expectation of II is equal to 1 times the probability of this event plus 0 times the probability of this event. And because this is 0, so we can ignore that. And probability of this event is actually equal to probability of II is equal to 1. Now, there will be a single type I coupon in the final set if a coupon of each type has appeared before the second coupon of type I is obtained. Meaning, if you want to make sure that type I is obtained for only once, we have to make sure that all the time of all other types of coupons have been obtained is actually before the time that the second coupon of type I is obtained, right? If this is the case, then type I coupon will be obtained for only once. Okay? So SI, if we let SI be the time at which the second type I coupon is obtained, then the probability of this event is actually equal to the probability of this event. And probability of this event represent Xj, which represent the time that type J coupon is obtained, has to be less than SI, which represents the time that the second type I coupon is obtained, right? So because if all the Xj less than SI, then actually type I coupon will be obtained only once in the final collection, right? And because SI, this random variable, represent the second type I coupon is obtained, so this is actually a gamma random variable with parameter 2 and the pi. Why this is pi? Because this type I is actually the arrival of type I coupon is actually a sub-Poisson process with parameter lambda pi, because the probability that type I will appear is actually pi, and the Poisson process, the grand Poisson process, has the parameter lambda. So based on the proposition we have learned previously, that is lambda times pi, and because lambda is equal to 1, right? So this is actually equal to pi. So probability of II is equal to 1 is actually equal to probability of Xj less than I for all j conditional on Si is equal to X and times the density function of X, and we take integration from 0 to infinity with respect to X. And then because Si is equal to X, so we can use the X to replace the Si here. And also because all the Poisson process J, coupon J, are actually independent, so this probability can be written as the multiplication of each individual probability of each individual process, right? So that is Xj less than X, this probability is equal to 1 minus exponential minus pjx, and we still have the PDF in the end. Now, expectation of summation II is actually equal to summation of expectation of II. And we know that expectation of II is actually this, right? and you have summation outside. Now we can swap the order here. So we first have summation here and followed by the integration. Of course, we still have the multiplication of this probability times the density function of x. And you can organize the equation and get the result. One question. What is the probability that n events occur in one Poisson process before n events have occurred in the second and independent Poisson process? So we let N1 and N2 be two independent Poisson processes having rate lambda 1 and lambda 2. Now we introduce two notations. Let S1n be the time of the nth event of the first process, so we put 1 here. And S2n represent the time of the nth event of the second process, so we have 2 here. Now, this question is actually asking for the probability of S1n less than S2n. But before that, let's look at other cases. When n is equal to n is equal to 1, then we are asking probability of S11 less than S21. And so basically we are looking at the first arrival or the first event of the first process that comes before the first event of the second arrival. The first event of the second process. And so this probability is actually equal to lambda 1 over lambda 1 plus lambda 2. And we have learned this result on slide page 17, right? And we know that, so for example, if you think about the first process like this, the lambda is higher, and the second process is like this, lambda is lower. So basically, if we are looking at S11 less than S21, basically we are asking for when will be what is the probability that the first arrival of the first process will come before the first arrival of the second process. And because the first process lambda is higher, right? So that means the arrivals will be more than the number of arrivals of the second process. So actually S1, the probability of S1 less than S11 less than S21 will be actually higher when this lambda is higher, right? So actually this probability is proportional to lambda 1, because if lambda 1 is higher, then this process has more frequent arrivals, right? So you will have higher probability that the first arrival will come before the first arrival of the second process. So that really makes sense, right? And the second case, how about the second arrival of the first process will be less than the first arrival of the second process? What is the probability of that? Okay, so basically we know that the first arrival of the first process less than the first arrival of the second process, and the probability will be lambda 1 over lambda 1 plus lambda 2. And after the first arrival of the first process, actually, because this is all of them are Poisson processes, so we have memories properties here, right? So this probability will simply equal to lambda 1 over lambda 1 plus lambda 2 to the power square, because after the first arrival of the first process, the process actually starts over again, right? So you have the second time you still have the lambda 1 over lambda 1 plus lambda 2, that the second arrival of the first process is more than it comes before the first arrival of the second process, right? Now how about S1n less than S2n, the probability of this event? And actually this event can be think of as n has will appear before m tails if one flips a coin having the probability of lambda 1 over lambda 1 plus lambda 2. So think about that. If the first process you have like 5 arrivals, and the second process you have 3 arrivals. So you are asking what is the first process, right? And the 5th arrival is less than the second process, the 3rd arrival. Okay, so actually you can combine these 2 processes like we have like this. Right, so totally we have 8 arrivals, right? And we don't need to care about the last arrival. So we just have to make sure that before the last arrival, we have at least 5 or more arrivals of the first process. Then we will have a probability of S15 less than S23, right? So that comes to the result like S1n less than S2m will be combination of n minus m, n plus n minus 1, because the last arrival we don't need to care, right? And choose k, and because this is each arrival is actually independent, right? So lambda 1 over lambda 1 plus lambda 2 to the power k times lambda 2 over lambda 1 plus lambda 2 to the power n plus m minus 1 minus k. And this k can start from n or even more to n plus 1, n plus m minus 1. Just like the example here. So if you have 5 arrivals here for the first process, and this is the second process, if you want to have 5 arrivals of the first process come before the 3 arrivals of the second process, you have to make sure within the totally 8 arrivals, before the last arrival, we have to make sure the first 7 arrivals, we have at least 5 arrivals of the first process, right? 5 or more. So that means 5, 6, 7, right? So that is like here. You have n to n minus n plus n minus 1. Okay. Conditional distribution of the arrival times. Suppose it is known that exactly one event of a Poisson process has taken place by time t. What is the distribution of the time at which the event occurred? So we are looking at the probability of t1 less than s, conditional on nt is equal to 1. So by definition, that is, the denominator will be the probability of nt is equal to 1, and the numerator will be these 2 conditions both satisfied simultaneously, right? So the numerator will be the probability because t1 less than s, so that means 1 event in s and t, and 0 event in s and t, because t1 less than s and nt is equal to 1, so there will be only 1 event in the between 0 and t, right? And also because 0s and s and t, there are 2 non-overlap intervals. So based on the properties of the Poisson process, we know that this probability can be separated as the probability of 1 event on S and T times the probability of just like this, probability of 0 event in S and T. Okay, so we can separate, so this probability can be separated as this probability times the probability of this. And probability of 1 event on 0 and S, because this is Poisson process, right? And between 0 and S, the lambda will be lambda S, right? Times exponential minus lambda S divided by 1 factorial, which is 1, okay? And 0 event in S and T. So 0 event in S and T will be exponential minus lambda t minus s, right? And lambda t minus s to the power of 0 divided by 0 factorial, that is 1. So we are left with only this, right? And so we cancel out, and turns out that the result will be s over t. So what does that mean? That means because Poisson process has stationary and independent increments, each interval in 0 and t of equal length should have the same probability of containing the event. So basically that means the time of the event should be uniformly distribution over 0 and t. So look at this, s over t, this is actually the Cdf of uniform distribution, right? So we know that this probability is actually a uniform random variable. So previously, we know that t1 less than s, conditional on nt is equal to 1, this probability will be s over t. Now, we want to study a more generalized version. So, if we have a sequence of random variables, y1, y2 up to yn, and we call y1, y2 up to yn order statistics, and the y bracket of k is the k smallest value. So, for example, if you have a sequence of random variables, so for example, y1, y2, y3, this is equal to 1, 2, 3, or 3, 2, 1, or even 2, 3, 1. Their order statistics, because order statistics always start from the smallest value and continue to the highest value, the largest value, right? So they are all 1, 2, 3. Okay, so order statistics just simply means that we order all the values from the smallest value to the largest value. So suppose yi is IID with density function little f. So f of y1 is equal to y1, y bracket 2 is equal to y2. This is actually multiplication of fyi times the n factorial. Why we have n factorial? Because based on this, we know that all the permutation of these values have the same order statistics, right? So we have factorial here. We have n factorial here. So if yi is uniform 0t, then f order statistic y1 is equal to little y1, y2 is equal to little y2. This is actually equal to n factorial divided by t to the power of n, because each random variable is uniform distributed, right? So that is 1 over t, and because we have n, right? So t to the power of n, right? 1 over t to the power of n. But because these are order statistics, so we always have to multiply to multiply it by n factorial, because all the possible permutations lead to the same order statistic, right? So we have n factorial in here. Theorem. Given that nt is equal to n, the n arrival times s1 up to sn have the same distribution as the order statistics corresponding to n independent random variables uniformly distributed on the intervals 0 and t. What is the proof? So the proof is like this. So if s1 is equal to little s1, s2 is equal to little s2, and nt is equal to n, because totally we given that nt is equal to n, right? So that means the first arrival time will be s1, and the second arrival time will be s2 minus s1, right? And the third and up to nth arrival time will be sn minus sn minus 1. And also because we totally will only have n arrivals, so the n plus 1 arrival time must be greater than t minus Sn. So meaning we have n, so you look at the picture here. So we have n arrivals here. And because totally we only have n arrival, so the n plus 1 arrival, the arrival time, this arrival time, Tn minus 1, much greater than T minus Sn. Right? Actually, this should be the density function because S1 and S2, they are continuous random variables. So the density function f of S1 is equal to little s1, S2 is equal to S2, up to nt is equal to n, and this will be the event like this, as we have explained earlier, right? And we know that T1, T2, up to Tn, they are independent random variables following exponential distribution, right? And this is their density, so we can just separate their density, write their density separately and put them together. And the probability of Tn plus 1 greater than T minus Sn is equal to this, right? Because Tn plus 1 is still exponential random variables, right? Now, the density function of S1 up to Sn conditional on n, by definition, that would be the denominator will be the probability of nt is equal to n, and the numerator will be the joint density, right? And this is the joint density, and this is the denominator will be the probability of nt is equal to n. And because nt is a Poisson random variable, so the probability will be e exponential to the minus lambda t times lambda t to the power of n divided by n factorial. And we can organize the equation, and it turns out that would be n factorial divided by t to the power of n. Simply a Poisson process. Suppose there are k possible types of events, and that the probability that an event is classified as type I event I from 1 to k, dependent on the time the event occurs. For example, if an event occurs at time y, then it will be classified as a type I event with probability PIY. And of course, every event will be classified as one of the k types. So summation PIY must be 1. Now we have the following proposition. If NIT represents the number of type I events occurring by time t, then NIT are independent Poisson random variables having means lambda times integration from 0 to t PIS ds. Recall previously we have a proposition like if we have a Poisson process and these are the Poisson arrivals, and we say if the arrival, each arrival can be classified as type 1 or type 2 with the same probability, for example type 1 with probability p and type 2 with probability minus p, then we say type 1 is a Poisson process with parameter lambda p, right? And the type 2 is still a Poisson process with parameter lambda times 1 minus p. But that is because all the p remains the same throughout the whole process. Now, if we say this p of the event will be classified as type I, will dependent on the time y, and we are actually looking at the time interval from 0 to t, then we say this parameter lambda p should be written as lambda times, because this y is a continuous variable, right? So you should take integration and dy y from 0 to t, because you are looking at the time interval 0 to t, so you take integration from 0 to t. Okay, so that is the proposition here, except for we use summing variable s instead of y. Okay, so because remember that now the time, this variable time is continuous. So instead of the same probability p, you have to take integration. And we still have a rigorous proof here. So probability of n1t is equal to little n1, n2t is equal to little n2, up to nkt is equal to little nk. And this can be written as the conditional probability that this n1 is equal to little n1 up to nk is equal to nk. Condition on nt is equal to summation ni times the probability of nt is equal to summation ni. Now we consider an arbitrary event that occurs in 0 and t. Then the probability that the event will be a type I will be classified as a type I event will be pi. Then pi can be written as, remember that this this probability depends on s, and because time is continuous, so we take integration from 0 to t and divide it by t, because we are looking at the interval between 0 to t, right? So the probability should be written as the integration, then divided by time t. Now, the conditional probability of this can be written as, remember that Poisson process, each arrival is actually independent. So this Poisson process, this conditional probability can be written as a multinomial distribution. So we have summation ni arrivals, right? But the first type will be n1, the second type will be n2, the k type will be nk. So this is actually a multinomial distribution. So we have summation ni factorial divided by n1 factorial, n2 factorial, up to nk factorial times p1 to the power of n1 up to pk to the power of nk. Now, this probability without conditioning can be written as the multinomial distribution, the PNF, times the probability of this, right? So that is this. Because remember that n of t is still a Poisson process with parameter lambda t, right? So the PMF will be exponential minus lambda t to the summation ni, because now we say nt is equal to summation ni, right? So summation ni divided by summation ni factorial. And so we know that that will be multiplication of this. Now we look at expectation of ni of t, and that is equal to lambda t pi. And what is pi? Pi is here, right? This is pi. So we put pi back in here, and we can cancel out t, so we can conclude the proof. We give an example here, an infinite server queue. Suppose that customers arrive at a service station in accordance with the Poisson process with rate lambda. Upon arrival, the customer is immediately served by one of an infinite number of possible servers, and the service times are assumed to be independent with a common distribution G. Notice that I didn't say G is exponential. G can be any distribution, common distribution, not necessarily exponential. What is the distribution of xt? Xt means the number of customers that have completed service by time t. And what is the distribution of yt? Yt means the number of customers that are being served at time t. So basically, every customer can be classified as type 1 or type 2. Type 1 refers to the customers who complete the service by time t, and type 2 are those who do not. So every customer, either you are complete service by time t or not, right? So basically, we can classify all customers into type 1 or type 2. So basically, for any customer who enters the service station at time s, like this, that the probability that the customer will be classified as type 1 is, so if this is the time point that you enter the system, and if you want to be classified as type 1, that means you have to finish the service by time t. So that means your service time must be less than or equal to t minus s, right? So that means your service time must be less than or must be less than t minus s. And because the service time distribution, the CDF is G, right? And less than t minus s, this probability will be g t minus s. So basically, by the previous proposition, we know xt is still Poisson random variable with parameter lambda times PIS, and we take integration from 0 to t, and PIS is actually gt minus s, right? Because that represents the probability that the customer will be classified as type 1, so I is equal to 1, and that is G, and this probability is GT minus S, right? And you can write that as lambda times integration 0 to t GY dy. How about YT? YT is still a Poisson random variable. So YT, recall that YT represents the number of customers that are still being serviced by time t. So by time t, that means you are still being serviced, right? So that means your service time must be greater than t minus s, right? So we can use g bar t minus s to represent the probability that you will still be, the customer will still be serviced by time t. So that represents g bar t minus s, that is 1 minus g t minus s, because that means, because this probability means the probability that the customer is still being serviced by time t, because the service time is greater than t minus s. So the probability will be 1 minus gt minus s, or g bar t minus s. Okay, and you can write that as lambda integration 0 to t g bar y dy. Know that ST and YT, the customers of type 1 or type 2 are independent Poisson processes, right? And of course they are independent. Further, we can consider the joint distribution of YT and YT plus S. YT represents the number of customers being served at time t. YT plus S represents the number of customers being served at time t plus S. Now, we have a picture like this. So this is time t, this is time t plus s. Okay? So basically, we can classify, previously we classified the customer into two types, right? Type 1 or type 2. But now we can classify the customer into 4 types. So for example, type 1, that means the customers enter the system before t and complete the service in TT process. Now I use this to make it more clear. So this is type 1. Then how about type 2? Type 2 means this, so this is T plus S. Okay, so type 2 customer means you arrive before time T. Okay, now I use a circle to represent the arrival of type 2 customer. So type 2 customer arrives before time t and complete service after time t plus s, like here. Okay? And type 3 means, so still we have t plus s. So type 3 means the customer arrives between t plus s, like this, triangle, and the complete service after t plus s, so like this. And the fourth type means otherwise, meaning the customers who do not belong to type 1, 2, or 3. Okay? Now what we need to do is to calculate the probability of each type. Okay? So for example, if the customer wants to be classified as the first type, that means you have to arrive before time t and the complete service in t and the t plus s, like this picture here, right? So that means I can use the service time must be greater. So the service time. So basically the probability will be g, like here, gt plus s. So if this arrival time point is y, so t plus s minus y. So that is the service time that can. So meaning if we use g of t plus s minus y, that means the customer that have service time from Y to T plus S, right? But actually, we want to make sure the customer leaves the system between T plus S. So you have to subtract the probability that the customer will leave between Y and T, right? So that probability is G of T minus Y. So that is totally put together. We can say the customer that be classified as type 1 will be G of T plus S minus Y. So that is, and minus G of T minus Y. Okay? Let me say this again. If the customer want to be classified as type 1, you have to enter the system in, for example, the time point Y, that is before T, and you leave the system between T and T plus S. So if you put G of T plus S minus Y, that is the probability that the service time can be less or equal to this long, right? But because you have to leave the system between T and T plus S, so this probability has to subtract that the service time is less or equal to this long. So that is T minus Y. Okay? And similarly, you can calculate P2. Okay, let's look at P2 here. So P2 means the customer arrives the system before T, right? And the complete service after T plus S. So if you consider the service time, that is T plus S. So this is the time point that the customer enter the system. T plus S minus Y, that is service time of this or less, of this long or less, right? But because you have to leave after T plus S, so that should be 1 minus the probability that the service time will be between T plus S minus Y, right? So you use G bar of T plus S minus Y, okay? You should think about these probabilities yourself carefully, okay? So if with these probabilities now, we can look at for example, the covariance of YT and YT process and the joint distribution. So if we let Ni mean the number of type I events that occur in 0 and T plus S, then by proposition 5.3, we know that Ni is still Poisson, right? With parameter E of Ni is like this, right? Now, because YT, that means the customer that are still being serviced by time T. So YT still serviced by time T, so that is type 1 and type 2, right? So that is that is N1 plus N2, right? But how about YT plus S? That means the customer are still being serviced by time T plus S, right? So that would be N2 plus N3, right? So that is N2 plus N3. So covariance YT and YT plus S will be covariance N1 plus N2 and N2 plus N3, right? And also because N1 and N3 are independent, right? So I can just cancel N1 and N3. So we are actually looking at a covariance N2. But covariance N2 is variance N2. But variance N2 is actually, because we know this is Poisson process, this is Poisson random variable, right? So the variance and the expectation are actually the same. So that is lambda and take integration from 0 to T, G bar T plus S minus Y dy, just like this. Just like the mean of N2, right? Okay. How about the joint distribution? So joint distribution means YT is equal to I and YT plus S is equal to J. So YT is N1 plus N2, that is equal to I, and the YT plus S means N2 plus N3, that is equal to J. And you know that if we let N2 is equal to capital I, then N1 must be I minus capital I, right? And N3 must be J minus capital I. But I can only from 0 to minimum little I and J, right? because capital I cannot exceed minimum I and j, because all of the n1 plus n2 and the n2 plus n3 must be positive, right? And you know n1, n2, n3, they are independent random variables, so you can separate the joint probability into the multiplication of these probabilities, right? And that's it.